So welcome everybody to the British Tunnelling Society's December evening presentation, and welcome to all those online. So I'll start off with the safety announcements. So please, can I ask you to silence your phones if you haven't already? In the event of a fire, alarm will continuously sound. Make your way to the emergency exits following the signs, and the assembly point is at the Westminster Arms, just to the side of the Westminster Arms. ICE staff will be on hand to assist. Do not use the lift. Anyone with mobility difficulties, they'll be taken to the venue's nearest wheelchair refuge point and assisted by fire wardens to safely exit the building. Once there, remain until the fire officer says we can safely go back. Okay, do we have another slide, please? Okay. Yeah, the picture says a lot, doesn't it? So, John Scoley, much loved figure in the tunnelling world and a man of immense warmth, humour and wholehearted spirit, passed away, leaving behind a legacy as colourful and enduring as the stories he told. So, earlier this week, I was informed by John's wife, Liz, that John had passed away at a care home in Tunbridge Wells following a long illness, which he tried to fight, but in effect, the chemotherapy didn't have an effect in the end. John was first voted onto the BTS committee in 1994 and went on to be co-opted to organise the annual dinner to what we now know it as. When it kicked off, it was nothing like it is now, and it's John's vision, panache, and energy that it is what it is today, and he'll be sorely missed. So quite a few people have wanted to put some words together, the impact John had on them. And Divik has kindly put a lot together. This will come out with the obituary, but I'm just going to pick out a few little bits from it. He began his career with characteristic enthusiasm on the Second Mersey Tunnel in Liverpool, forming friendships and professional bonds that would span nearly 5 decades. His work took him across the UK and around the world, from the A55 Pennyclip Tunnel in North Wales, where he served as resident engineer, to the Dublin Port Tunnel, to significant overseas projects, such as the Mirka hydroelectric scheme in central Java. Wherever he went, John brought not only his technical expertise, but a rare ability to unite people. Colleagues recall that under his inspiring leadership at Micra, the client, consultant, and contractor worked in true harmony, an achievement many describe as a high water mark for the team. So, yeah, I mean, my recollections of John are all about town crying, and the annual dinner and the waistcoats. But those who know him before I got to know him stressed that he was a very good engineer and very competent. So his passions outside engineering were equally vibrant. A folk musician, he played in the band called Thingamajig, often breaking into song mid-conversation to make a point. He was a spirited caller at town barn dances where local and international and dedicated performers and organisers of Morris dancing. Many remember him striding across a cold Leatherhead office car park during a fire drill in February, accordion in hand, lifting the spirits of 200 shivering staff with folk songs and country tunes. That was John, wholehearted, unfazed, always mucking in. His creativity and sense of adventure seemed to have no limits. During his time in Java, he famously arranged for a full steam train excursion, complete with 6 carriages, ready and waiting outside the construction village one Sunday morning. Families boarded with picnic baskets and blankets, embarking on a day so magical that colleagues still speak of it with disbelief and delight. It was the kind of experience only John could have imagined and made happen. So, several years ago, Ivor Thomas asked me to assist John in organising the annual dinner, I guess with this day in mind, because for many years the annual dinner was just John Scoley. It never happened. It wouldn't. No one knew anything apart from John, and he was the one that made it all happen. So it's given me the opportunity, which I'm very thankful of, to get to know John and Liz better, and visiting him a few weeks ago. And we brought him that picture down and a little crystal as well, which at the time I don't think John fully appreciated, but as in he wasn't fully with it. But the family should certainly get much comfort out of the support the British Tunnelling Society are giving them at the moment. So the funeral arrangements have not yet been announced. If anyone would like to make personal contact with Liz, then if they contact the British Tunnelling Society, we can provide an email address. Okay, so moving on to tonight's presentation. 20 years ago, I sat where you are now, and I listened to Colin give his Harding Memorial Lecture and his vision for the future of tunnelling. It wasn't recorded, that lecture, but there's three things I remember particularly about it. One was an image of the Thunderbirds. The second one was TBMs. TBMs powered by mini nuclear reactors. And the third was a TBM capable of creating its own lining as it passed through the tunnel. So we're about to hear that Colin hasn't forgotten that vision. So I'd say it's a rare thing to hear the word revolution in a BTS evening presentation. Colin is an internationally recognized expert in tunnel design and construction with over 40 years of experience. He has contributed significantly to the sector by developing numerous innovations in tunneling and underground space, which have been credited with improving the safety, efficiency, and sustainability of many recent projects. Today, he and his organization, CECL Global, provide expert support and advice to clients around the world. And he manages an active research and development program in collaboration with industry partners and the University of Warwick. Dr. Henry Paradu has over 14 years' experience in engineering design, management, and research for major infrastructure and tunnelling projects. His major project contributions include Lee Tunnel, Thames Tideway West, and the UK's geological disposal facility for radioactive waste. Recently, he has completed a PhD at the University of Warwick, researching novel materials for slipform tunnelling. So, Colin.
Well, good evening, ladies and gentlemen. The room's not full, but the quality is certainly here, and I'm so pleased to see so many old colleagues and friends and people I really respect. This suit has been coated with tomato-resistant materials, so hopefully we'll crack on anyway. So John mentioned the Harding Lecture, and as a number of you know, I've been banging on about extruded linings for a long time. The difference tonight, however, is when I spoke at the Harding Lecture, I just thought it was a good idea and that we should do some further work. And when I spoke again in 2015, I didn't have a solution. I was just suggesting, look, this is a really good idea and we should do some work. And in fact, we formed a number of consortia and applied for government funding to do exactly that. And unfortunately, we failed each time. And so I got to a point of thinking, look, if this is ever going to happen, I'm just going to have to fund it myself. And we've spent, as a company, we're not a big company, but we've spent 20% of our annual turnover, about 40% of our profits on this research. So, we kind of invested in it, and we believe in it. So if we just look at the historical context, you're probably all thinking, well, I've heard all this before. Haven't they? Extruded linings have been around a long time and they've never worked. So I think that was Colonel Beauford's Channel Tunnel, I think 1880, something like that. It wasn't an extruded lining, but it's a nice picture. So arguably the sort of start of this discussion is with Mark Brunel, who I'm sure you all know spoke about the process of tunneling around the shipworm and how that shipworm would gnaw at the timbers and it would extrude a lining behind it. So I suppose that's the sort of inspiration, and he took that as inspiration for his patent, which actually looks nothing like the tunnel shield that he used on Rotherhithe, but nevertheless was the inspiration. And some of you may be surprised to know that extruded linings go back a long way. The Russians actually, the research that we've been able to do on this over the last 6 years, the Russians in the 1960s were the first. And, we want to be very respectful of what's gone on in the past. And we're standing on the shoulders of what other engineers have done. One of the issues, of course, in the 1960s is that they only had normal concrete. They didn't have any of the wonderful admixtures that master builders can provide nowadays. So they had pretty much normal concrete. And so this process was a jump shutter, so basically erecting a shutter and placing concrete behind it. So there's absolutely no benefit to the industry at all compared with a segmental lining. If we move on to some work done in America, now this was quite a serious piece of research, which actually wasn't well publicized by Foster Miller. Now this was truly a slipform shutter, but again, they were trying to make accelerated concrete work. And as you'll hear today, we've decided to take a completely different approach to this. So there were many good things that came out of this, but at the end of the day, they threw the towel in, it didn't work, and it was no benefit to the industry. We then move on to the 80s, and Hockteeth, as a number of you will be aware, spent considerable time and effort looking at extruded linings, and they built a number of projects. But they weren't the most efficient. They certainly didn't break any speed records, and the quality of construction was not acceptable. If we move on to more recent examples from Japan, extruded linings have been used relatively recently, but again we've got shutters which are being disassembled and moved to the front. And so really you've got to ask yourself, well, what's the benefit? You might as well just build rings. And I think this is a really key issue that over my career, as John has mentioned, I've been fortunate to be involved with people that have, and we've been able to do new things, but it's got to be a benefit. It's got to be more cost effective. It's got to reduce the carbon. It's got to be safer. There's got to be a benefit. And unfortunately, the experience of extruded linings up to this point was, perhaps building us to the point we now are. We've got new materials, we've got new ways of doing things. And so perhaps the time has come. I don't think this one got off the drawing board. Again, accelerated concrete. And probably the most recent a relining system is using effectively an accelerated sprayed concrete and a form. So what we're going to talk about this evening is completely different. And I should say right from the start, we're not flying any kites here. We absolutely believe in what we're presenting today, and we genuinely believe that this is a viable method for the future. We know existing technologies. I quite often followed a vehicle up I think the M5. I'm not entirely sure where the segment was cast, but an Arctic truck carrying one large segment, a precast segment, and you're thinking, how inefficient is that? And we all know in rock tunnels, we have the issues of using sprayed concrete and bolts and the waste factors and all sorts of issues. With precast concrete rings, which of course, of course, we've deliberately picked a very bad example of some damaged rings, but we all know that it's possible to damage the rings. And what we're trying to do is simplify the process, reduce the waste, and reduce the damage. But there's three challenges that we have to face. First, the formwork. So the formwork is traditionally for extruded linings was not a slipform lining. It was disassembled and reassembled. So labor intensive and of little value compared with conventional technology. The materials, a lot of the work that's been done on extruded linings was done before the advent of high quality fiber reinforcement and the concrete admixtures that we use today. And the quality, we've not been able to find any examples of defect-free extruded linings. So, you know, that's where we're at. So we took a fundamental rethink about how we're going to look at this. And without wishing to steal Henry's thunder, what we're doing is producing an instant structural lining. So it doesn't rely on any chemical process or hydration of cement. And what we've done is look at two different systems. So the asynchronous, which means it lines the tunnel as you're excavating it, and the excavation process could be with a backhoe, it could be with a road header, it could be a full face TBM, it could be a slurry shield, an EPB shield, a variable density shield. The front end, the digging bit, is existing technology. What we're replacing is the lining. So we're getting rid of the precast concrete lining and the grouting. But there's also a non-synchronous, which is meant for relining existing tunnels. And at the heart of this is something we call the injector. So it looks a bit like a concrete pump, but it's not. It hasn't got an interference fit. It's designed actually to squeeze water, a small amount of water. And again, Henry will go into more detail, and to compress the material to form the structural material. It can be used for any profile. So one of our partners has got a long history of building TBMs which are non-circular, so triple-headed or double-headed TBMs. So pretty much any of those profiles could be used. If we just look at the basic pillars, there's two parts to the process. My focus has primarily been on the equipment, and Henry, for the last 6 years, has been making lots of mud pies at the University of Warwick and torturing lots of samples, and he'll talk about that in more detail. So if we just show a visualization, so the front part of this machine, the one part can be any conventional excavation process. The red pipe is the concrete supply pipe, and the blue pipe is a continuous flushing and cleaning system. So one of the challenges, and I expect to get lots of challenges today, is that we all know that tailskin grouting systems are the bane of tunneling contractors' life. They keep blocking, they cause lots of delay. And in fact, one very reputable TBM manufacturer, the informal feedback we got when we approached them about this, concrete and TBMs don't go together. And we absolutely agree with that. We absolutely agree with that. And that's why having an integral cleaning system, which is actually part of the system and systematically done, we think is really important. So what you saw there was the synchronous machine. And this machine, to enable the process to get sufficient pressure to be able to place and crush the material in place, there has to be a resistance. And so those wheels, or they can also be skids, depending on what the nature of the substrate, controlled by fuzzy logic. And we've ruthlessly abused the master's program at Warwick University to look at all of these things. So looking at fuzzy logic to control the load in those wheels, because of course, you know, what we're trying to do is have a self-centering system that'll follow a theoretical set of coordinates, irrespective of where the substrate is, within reason. And you can see here that the reason that the injectors are vectored is that we don't want to generate too much forward propulsion going to the left-hand side of the image. And so for the non-synchronous, that's why we've got the incline injectors. And sorry, one of my team, we spent quite a lot of time on doing these visualizations. And the purpose is rather subtle, but you can see that the wheel is sort of going in and out, and they're hydraulic actuators which are designed to self-center the system, but also to apply the braking. So yes, there will be drag on the shutter, but actually it's not going to be that huge. So we need to provide another restraint force, and that's where those wheels or skids will come in. The shutter, there's a little printed model that we've got here. This pretty much for any size of tunnel, we're expecting the shutter would be 3 meters long. So whether it's 16.5 meter diameter or 3 meters in diameter, and the shutter's articulated, obviously, because it needs to go around corners, but it's passive articulation. So at the end, you'll see there's like some hydraulic rams. So the high tensile McAloy bars or Dividag bars run through the length of the shutter. Those actuators are coupled in series. So all of the load in each of the bars remains exactly the same, irrespective of how long the bar is. So we think that's really important because obviously we've got to go around curves, and we need a passive dumb system. So at the heart of this machine is its simplicity. It's absolutely simple, and it's been built such that every component could be replaced underground if necessary. If we just look at the balance of forces, so the only thing that's moving this machine forward is the actuators. And there are quite a lot of them. So for a typical shield, there could be, in fact, we kind of default to 49 actuators. So there are a lot around the perimeter because we don't want them too far apart. And those actuators have got to provide enough forward propulsion to overcome the thrust on the cutter head, the drag on the shield, the drag on the shutter, and the fairly nominal loads that would come from any trailing gear. And if we just look sort of in real time, so the typical stroke for the injector would be about 300 millimeters. So it's actually very little concrete, very little and often. And the speed you're seeing this animation is probably, this is probably the sort of speed if we were advancing a TBM at, say, 50 millimeters a minute. So, most of us would be pretty happy at 50 millimeters a minute. The whole system, however, has been designed for significantly higher advance rates. But of course, for the synchronous system, that depends on how quick we can excavate the tunnel. A really important part here of the design is the length of the injector head. So that bit of metal at the front, the reason it covers the supply pipe is that obviously we don't want to just press the concrete back down from the position that it came. And then at the end of the cycle, being overdriven such that there's the whole system will go into flushing mode for cleaning purposes. If we cannot clean this system, it will be hopeless. It will never work. We're not using concrete, but it's quite similar, and it does have some Portland cement in it. So we've got to keep the system clean. And if we unwrap the system, and this animation is a little bit crude in that it kind of shows all of the actuators moving in and out at the same time. This is not correct, actually. In reality, each injector has simple laws that it's given. And the simple law as it's given is it continues to push until it gets to a maximum pressure, and then it stops. And its next law is if it gets to its full extension, it returns. And its final law is if it's been told it's going into cleaning mode, it pushes an extra 100 millimeters further. And so the rate of advance of the machine is governed just by one parameter, and that's the speed of the forward stroke of these injectors. And if we just come back before I hand over to Henry, the chief engineer, and I think probably the person that's best known and associated with extruded linings, he said, and I think Shaney did a great article just looking and reviewing the work that he did. And as I say, we're absolutely standing on the shoulders of these people in anything that we're proposing today. So he's basically saying, well, why bother with an extruded lining? If you use an extruded lining, you've got to put a secondary lining in, and you'll need a waterproof membrane. So what's the point? And you're probably thinking, why have I shown that quote? But he also said that if the concept was to be revived, then you'd have to start from scratch. And we'd have to take advantage of modern tunneling technology, modern concrete technology. And so with that, I'll hand over to Henry.
Thank you, Colin. So the starting point for our research and development into a slipform tunnel lining material, STLM is the acronym that I'll probably keep referring to, is the requirement. So what does this material fundamentally need to be able to do at each stage in the process? So firstly, it needs to be compatible with the slipform tunneling process, and this has been some iteration with the equipment design and development, as well as the material research and development work. And the material also needs to be commercially viable. So this means that consideration of component costs, embodied carbon, material availability have been very important to the development. And we know from the outset of this process that it'd be unsustainable for the process to rely on expensive or exotic components which have, say, poor global availability. And a key part of the development has been consideration of the mechanical properties. But we've also been mindful and done a holistic systems engineering type approach to this development to ensure that the material satisfies requirements on things like the fresh properties and long-term durability, as well as the logistics implications of actually constructing this underground. So it's been a 5-year research program to develop the STLM to where we have it today. And in order to effectively test the material, we've developed bespoke equipment to simulate the injection process and understand the properties of the material post-injection with physical research carried out at the University of Warwick. So we developed a bespoke arrangement to simulate the conditions of injection at full scale in the laboratory. So using a 100-ton servo-hydraulic actuator on a modular reaction frame, we're able to form large samples, so 150 millimeter diameter, 300 millimeter high samples under pressure as part of our development work and testing work. So we've designed our forming equipment, this sort of simulated injector, as a split cylinder. This split cylinder heavily reinforced to keep its stiffness, bolted sections together, which can be rapidly demolded following forming, has a common base plate to this system, and then we can test it quite quickly after forming in either an unconfined or a confined triaxial testing arrangement. So more recently, we've developed a sort of smaller, slimmed down version of this rig, which allows forming of smaller samples for material characterization, or benchtop forming rig. It's a rig that can fit in a standard compression test machine for concrete and can be handled by a single person. So it allows more samples to be made in one working day, and been very useful for some of the more recent mix optimization trials we've done. And looking forward, could be used as a production quality assurance tool as well. So onto the STLM mix itself. So what we've developed is something that is flowable in its fresh state, but upon application of this injection pressure, it immediately gains strength and stiffness through mechanical processes rather than a chemical hardening process, so densifying the material in situ through that high injection pressure. So the mix itself has many of the components you'd see in a conventional concrete, so aggregates, cementitious binder, water, steel fibers, polypropylene microfibers, but it's formulated in such a way that it's enhanced by this mechanical process to give us this very early age strength and stiffness. So the binder component of it uses Portland cement, which is replaced with partial replacement with limestone and calcined clay, supplementary cementitious materials, and overall has quite a low Portland cement content. We've deliberately moved away from using GGBS and fly ash as SCMs for availability, cost, and sustainability reasons, and preferring the LC3 type binder that we've been using. So when I talk about very early age strength and stiffness and mechanically derived strength and stiffness, what do I mean by that? So we've done some isothermal calorimetry studies on the binder part of this mix. And what that shows is circa 10 hours, we start to get the main hydration reaction happening in the initial setting of this material. It's about 10 hours. So we've been doing our very early age tests at less than 2 hours typically from mixing. So this is well before this initial set and the main chemical process kicks in. And that 2 hours is basically as fast as we can strip and demold the sample from the equipment and set up the strength test. So the results at this very early age are really mechanically derived strength and stiffness purely from that compactive effort. So this isn't me just having had too many cups of coffee. This is a sped up video of the whole test process. So this is from mixing the materials right through to forming the sample. So we've put a lot of instrumentation on this rig, so we're controlling the deflection rate to simulate the injection process with the servohydraulic actuator, measuring the stresses in the sample, recording these with the data logging system, looking at even things like pore pressure within the sample. This is essentially almost like an odometer test. What we're doing during the forming process, and I've definitely got a stronger right arm from doing all these bolts up hundreds of times in the lab now. But you'll see when I strip the sample, this is what we're forming very rapidly. So it goes from a flowable concrete through to something with appreciable strength and stiffness instantly because of that high compactive force from the injection pressure. So on to looking at the mechanical performance that we've observed in the testing. So the material exhibits a stress-dependent shear strength behavior from the triaxial testing that we've done in the very early age. This is also sub 2 hours after water hits the cement, as well as stress-dependent stiffness and ductile behavior as well in this material. So this can be fitted to the well-known Moore-Coulomb relationship and strength envelope, where we've been able to demonstrate a significant cohesion to this material, as well as a high internal angle of friction for the material at very early age. If we look to longer term, so when we're expecting some hydration from the binder components, we achieve a good strength gain in the first 24 hours, so exceeding that required by the modified J2 strength curve, and structural concrete behavior in the longer term, where the chemical hardening of this ternary LC3 binder system has been working very well, even at high replacement levels. So we've done validation as well in numerical studies and finite element studies, 2D and 3D. So using the results of the physical testing in forming an advanced constitutive model for the STLM, running simulations at tunnel scale, and looking at strain-based considerations as well to understand its performance in the real world. Onto the robustness and durability aspects and the testing and analysis we've done here. So firstly, a qualitative look at the STLM structure from peering inside these samples using X-ray CT scanners from some assistance from the National X-ray CT Centre, which has a base at the University of Warwick. So it's apparent that the STLM samples they're tightly packed, a high aggregate ratio in their compressed form and low porosity, and a high density of 2,500 kilogram per meter cube or higher. And this qualitatively suggests that the lining would be very durable in the long term. But then looking to more quantitative aspects of durability and durability testing. So we've done shrinkage testing. So shrinkage is obviously a very important consideration for a monolithic tunnel lining. So samples of STLM, formed STLM samples have been monitored for shrinkage for nearly 3 years now, and compared to some conventional cast concrete samples. And we've seen good results with when the STLM is compared to these in terms of low shrinkage. And with these long-term shrinkage strains that we're seeing, if we consider that in a restrained tunnel situation, we'd expect the lining to be uncracked in the long term from shrinkage strains, which is a big positive in terms of the water tightness and durability of a slipform tunnel lining. So abrasion is another durability concern, which is particularly for hydraulic tunnels, and we've undertaken a modified version of the ASTM C1130 underwater test. So this is where a sample is submerged in a steel tube. We put some varying sizes of steel balls on top. It's underwater. A motor and a paddle spins then this arrangement at 1200 RPM to generate an abrasive action. We leave that running for 7 days, like a mini washing machine. And we measure the mass loss from the samples because of that abrasion. And we found comparable performance to fiber reinforced structural concretes. Sulfate testing, so sulfate attack being a durability concern in certain geological environments. And we've done modified ASTM C1012 testing, where we've submerged samples in a strong sodium sulfate solution and looked at their length change and measured this over time. So we've been doing this for over 800 days now and have seen very low expansion from the STLM samples in our monitoring to date, and it compares very favorably to control concrete samples and visually as well. You can see in the bottom left there, the control samples are showing visible signs of distress, whereas the STLM samples are remaining almost as good as when they went in. Looking at water penetration testing, we've done water penetration testing on samples to give an estimate of permeability. So owing to that high density, low porosity of the material, the measured the calculated permeability from the water penetration test has been is very low. I've had a few questions on what happens after stoppage and whether or not there'll be a cold joint in the past for this process. And so we all know that the inevitable happens in tunneling, and stoppages are a part and parcel of that. So to answer this, we formed some samples in 2 halves. So forming half a height sample, leaving it for 7 days, then coming back and forming a second half of the sample on top to create a joint in the sample. So the high pressure in the process means that these joints are very tight and essentially invisible. Early water penetration tests have also indicated that these joints aren't forming any sort of preferential water path as well. And so coupled with other features of the process, so castellated profile of the injector bulkhead and the large number of injectors, giving us plenty of power to restart, and the longitudinal thrust that's provided on the lining at restart, means we don't think there'll be an issue with stoppages and restarting a machine in a slipform tunneling process. And a final word for me before I pass back to Colin on standards compliance. So the way we've designed and developed this material has been novel, but we've also been mindful of standards and standards compliance for assurance purposes. So the binder itself, the LC3 ternary binder, complies with the N197 Part 5 in the UK and Europe. And the recent BSI Flex 350 standard in the UK also gives us a performance-based route to compliance for novel mixers. And all of the mix component parts are standards compliant as well, used commonly in concrete mixers today. And that further provides assurance to the quality of the mix as it's used in a slipform tunneling process. So with that, I'll hand back to Colin to talk through some benefits.
He's a class act, isn't he? So, right, so what's in it for contractors, consultants, clients? So we're going to start by talking about cost. And before I start talking about cost and carbon, I should just mention that we've been very privileged as an organisation to have been commissioned by National Highways to build cost and carbon calculators. And those calculators have been used to set the affordability limit and the budgets for projects like Lower Thames and Stonehenge. So the purpose of saying that is that, you know, we're not a bunch of academics here saying if this is going to save you X, that this is a fantasy. We're just plucking figures. These are using exactly the same metrics and parameters that we would use to set these budgets. So if we just look at a couple of reference projects, we've got a rail project and a water project. And if we take High Speed 2, typical sort of proportions, 400 millimeter precast segment, 200 millimeter, because we all know the overcut on TBM seems to get bigger each year, and an internal profile of 8.8 meters diameter. If we look at the slipform alternative, we have a much smaller excavated diameter because, as we know, a lot of the ring thickness in a precast ring is to accommodate things like the gaskets and the fixings and you know, thankfully we're moving away from bolts now, but you know, the thickness is seldom governed just by the MN diagram of the lining, and so the equivalent in a slipform alternative. We're confident this is a one-pass lining, a watertight, structurally integral watertight lining. And of course, the internal diameter has to be the same. The second reference project, and this is a little bit, you know, I'm sure most of us in this room would have hoped that Thames Tideway hadn't put the secondary lining in, but they did. And so we'll benchmark against that. So in comparison, the slipform alternative, again, much smaller excavated diameter because we're getting rid of a lot of the processes and a single pass watertight high integrity lining. And what does that do to the cost? Well, we've looked at both the material cost savings and the total cost of construction. So the total cost of construction benefits from the increased speed of construction, the reduced number of personnel, and the reduced, obviously the reduced material quantities themselves. And the saving we have calculated is 50%. So you might think, well, how can just the lining process save 50%? Well, it's because we're saving the personnel, we're going faster, and we're reducing the materials, we're eliminating building rings, we're eliminating the grouting process. If we look at sustainability, the same with carbon. So the STLM has a certain amount of Portland cement. We couldn't get it down to zero, but we're using very sustainable materials. And as Henry explained, the use of LC3 calcined clay. It's not big in the industry at the moment, but there's the old English China clay quarry in Cornwall that's got the capacity to produce as much as the industry can use. And we all know that slag and PFA, you know, the world is fighting over the dwindling resources. And of course, we're not making steel and burning coal in the UK anymore. So, you know, it's going to come from overseas. So when we turn the handle using absolutely agreed parameters for all of these materials, we see a 50% reduction in the carbon. Potentially, and we see this more, not really as yes, it might be a sustainability issue, and it might be a cost issue, but it's a really good news story for a client. If a client can say, you know what, we're digging this tunnel and we're reusing the spoil to be able to build the lining, in reality, it doesn't save a huge amount of money. It might save, you know, 10% of the excavated material instead of going it off-site. So for projects like Glendo, which we've got a keen interest in, you know, we would like to look at, you know, whether the metamorphic rocks from that site could be processed. There's one thing that Henry hasn't mentioned is that there's some alchemy that happens when you crush these aggregates. So the mix you saw that picture of a really stony, bony, horrible looking mix. That's before it's crushed. When it's crushed, it tends towards a fuller maximum density curve. So there's this amazing thing that happens in nature that when you crush it, it's actually forming the perfect, and that's why it's so dense. So, you know, it might be only 1 in 10 projects, so you might be able to use the materials. And of course, we know there's all sorts of processing licenses, but potentially we see it as a good news story. If we look at the steel fibers, for years we've worked with Beckart as in my former life, and I should say that Henry and my other colleagues all used to work for me in my former life, and Beckart have made some real strides forward in looking at recycled fibers. So you're probably all aware, for years and years, people have been trying to chop up car tires to recover the high carbon fiber from that. Beckart believe that they've cracked that process. So it's just another possibility of bringing greater sustainability. If we look at safety, we know that the safest thing you can do in tunneling is to eliminate a process. So if we look at what we're not doing, we don't have any rings, we don't have a segment factory, we don't have the repetitive strain injuries that we're often seeing in those sorts of facilities. We haven't got to fit any gaskets, we haven't got any bolts to install, we haven't got any grout, no grout blockages, we don't have any secondary lining or waterproofing measures or shotcrete or rock bolts. And we expect that this process will lend itself much more to automation. Of course, there are going to have to be people in the tunnel to extend the services, and we'll look at and of course the huge issue now is the logistics, which I'm going to turn to. So we would see whether the driver is on the surface or in the tunnel, it doesn't really matter. But there is definitely an opportunity to greatly reduce the number of personnel within the tunnel. So we're reducing a number of processes. We're not building rings and we're not grouting, but we need real-time verification of the quality. We know we're suggesting that this process could be suitable for any size of tunnel in pretty much any ground condition, whether it be water-bearing sands or gravel or hard rock. If there's a holiday, if there's a window in this lining, then that's a catastrophe. So we've been working very hard at looking at how we can guarantee the quality of that lining before it appears out the back of the very short shutter. And bearing in mind at its maximum advance rate, that's 30 minutes after the point it was placed. So we've got some very bright colleagues at the University of Warwick who've got a number of ideas about how we can systematically measure the integrity of and make sure that there are no gaps. And one thing I haven't sort of majored on, if you imagine you're excavating through, say, a cast limestone with holes in it, or you get overbreak, this system is very similar to a pressure grouting system. The machine cannot move forward until it's filled any void on the outside, and each injector it's got its 3 little laws, and it just does its own thing, and it keeps pushing concrete in until it gets the back pressure. And we all know that interlocked machines, grout interlock, is normally the first thing that the miners turn off because it keeps stopping the machine and it stutters. And but we and our partners believe that we can resolve that. So if we look at the speed of construction, I don't know why we say 100 mil a minute, because you could go as fast as you like, as fast as you could supply the concrete. But 100 mil a minute realistically is the fastest excavation rate. If you were relining an existing tunnel, I think you could go even quicker than this. And one thing I should say is that these animations all appear as if it strokes, it moves forward and stops. It would actually be a continuous process because all the injectors are working together. But for the purpose of the animation, that's why it keeps stopping. We have undertaken extrusion and injection tests, and the primary purpose of this was to try to understand that if you're pressing effectively a wet concrete into a confined space, what lateral pressure will it exert on the shutter? What is the friction? So this enabled us to quantify both of those things. And also, we've done extensive work on looking at the durability of the steel components which are in contact, the shutter itself, and the injectors. And it is amazing if you look at concrete pumps, which are, they work at comparable pressures, a little bit lower, but they have incredible durability using special steels. If we look at the control system, we're working with our partners. We're civil engineers. We're just simple tunnelers. We're not mechanical engineers. But when we look at these processes, what is set at the beginning is what face pressure do we need and what rate of advance. So they're the high level controls. And then the system will automatically, the injectors will work with the one variable that they have, and that's the speed of the advance. And if we're going at sort of 10 mil a minute overall TBM advance, then the injector speed will be probably 1 or 2 millimeters a second. If at the higher rates, it'll probably be around about 10 millimeters per second. So these things are not running anything like the speed of a concrete pump. Henry's what you've probably seen there, and I haven't explained at all, sorry, is how in a simulated environment, by varying that advance rate and the face pressure, you can see that it turns the injectors on and off. Logistics, this is, I think, personally, is the biggest challenge. If we want to go, if we want to look at supporting, world-class advance rates, and our partner, which we'll talk about in a minute, they have 15 of the 18 world tunneling records at different sizes. Most of those, I'd have to say, are for unlined tunnels in rock. But with this process, what we're suggesting is that actually, it is only the excavation process which is governing your overall time for construction. So if we look at the construction, we are not suggesting that we pump this material long distances. So we're hoping this system will be used for 5, 10, 15, 20 kilometer tunnels. There is no way that we would suggest pumping or stage pumping a wet, effectively concrete, those sorts of distances. So what we're proposing is that the coarse aggregates and the sand are taken to the face in conveyors, and the cementitious component and the water is in a slurry. So the little video you saw of Henry and my other colleague Era looking at the viscosity and the rheology of these grouts is that we're absolutely confident that the open time for these grouts will allow us to pump the cementitious materials to the face and mix with the aggregates at the face. If we just look at a number of years ago, I worked for the Hyperloop technology company in California. I say worked, that implies getting paid. I didn't get paid. And at that time, I said, well, you should really look at slipform tunneling. I think it's so I gave them everything I had on slipform tunneling way before we started any of this. And they asked me a question, have you got a patent for this? I said, no, I'm just collected what's in the public domain, and I'm just saying you should look at it. Thanks very much. There's the door. And that taught me a real lesson that if you want people to take you seriously, then you've got to have IP. I mean, perhaps if I watched Dragon's Den and stuff like that, I'd know that. And so we have worldwide patent protection on this. And any of you that have tried to get a patent, and you might think, oh, blimey, they're doing this for 60 years. How's he achieved a patent? The reason we've got a patent is what we're doing is completely different to anything that anybody has tried in the past. If we look at our Slipform Tunnelling Consortium, you all know Robbins. They've been through a hard patch. They've bought themselves back from the Chinese, and they're doing very nicely now. Beckart, we all know Beckart, Master Builders, Ugitech, Kawasaki, and Hitachi. Kawasaki and Robbins have a pedigree going back to the Channel Tunnel. So, you know, then they have an ongoing collaboration. So we think we've got some pretty serious partners. And just before I sort of conclude, there are some acknowledgements I'd like to make. Certainly the support of our consortium partners. For those of you that know the Robbins company, that you'll know Locke Home, and Locke has been incredibly supportive, and his chief engineer, Brad Groth, and Beckart with Benoit de Riva, and my good friend John Greenhouse. They're always very supportive. Master Builders, I think Richard and Andrew are in the, so, you know, really thank them. And UGTech have also been very, very helpful. I'd also like to thank my colleagues, Dr. Era Hover. So she did the heavy lifting on producing the cost and carbon calculators. And that, I should explain, that was a 3-year commission from National Highways, where we were able to engage with labour suppliers, material suppliers, the plant and equipment. And a lot of the people in this room very generously gave information. And Richard Heaton, who did the visualizations that you've seen today, our patent lawyer, is an absolute star. Our precision engineer. So all those machines that you saw Henry using, everything had to be designed. Henry's designed all those from first principles, and we've had those fabricated from first principles. Our material suppliers, Breed and Aggregates for the aggregates and the cement, and Imeries, who are the suppliers of the LC3 materials. Now, at the moment, LC3 is not, and I'm sure I'm going to get loads of questions from Charles Allen about this. You know, it's not emerging technology, but it's chicken and egg. If the industry is going to use it, they'll produce more. And the University of Warwick, I kind of mentioned, and I think this is getting recorded, so I shouldn't say this, but student projects, we've got massive value out of using really high quality students to look at you know, the durability of these materials, or looking at the extrusion, looking at the steels and the abrasion. So I'd like to thank those. There's some people as well I've left off here, and that's my 4 children, because they've inadvertently invested their inheritance in this. I don't think they'll be watching, so it'll be fine. So what does that mean? Conclusions and next steps. We think, and you might not think, I hope you're a little bit more convinced than at the start of this, we think this works. We really genuinely think this works. And this could be a paradigm shift in how we build tunnels. And it's not, as I say, we're standing on the shoulders of people that have been trying to do this for 60 years. And this could absolutely change the investment decisions and how we look at choosing a tunnel over something else. So Keir Starmer has said, you know, electricity distribution in the Highlands, it's going on pylons, get over it because it's too expensive to, well, perhaps if you reduce the cost of tunnelling, that might not be the case. We've got Roger Miles in the audience. Some of you may know Roger. Roger, for over 20 years, has been promoting underground freight transport, something I'm absolutely passionate about. And I know companies like Arup and other organisations have also looked at this. You know, that could be a real, if we can construct these spaces much cheaper, and also convince, and I know Bill Gross in the audience, is, you know, convincing people that tunnelling is not hugely expensive. Yes, projects that involve tunnelling are hugely expensive, but you all know that the reason for that, and it's not actually the tunnelling itself. So that's the good news. However, we need a client partner that has the vision and the courage to adopt this. So we've met with SSE, and we've met with I say a limited number of people. But at the end of the day, until we have got a real world proof of concept tunnel built, we know that nobody's going to accept laboratory trials. So that's why we're working with Robbins to build a prototype. The design is in place, and we're looking for a client either in America or the UK. It's probably going to be a repurposed Robbins machine at about 3 meters diameter. So it's not, you know, it's not huge, but it will give us the opportunity to do a proof of concept. So thank you very much for your attention. And Henry will happily answer any questions.
Okay, could you knock the lights down a little bit, please? And then we'll take questions. Yep.
Good evening, Colin.
Be kind.
First question, after that entire master's at Warwick, it was great to have questions answered from you. Brilliant innovation and lecture over here. My question is about turning. It's good about like when you move in straight lines, but how do you actually turn the machine? You will have eccentric thrust acting. How does the slip form curvature happens?
Yeah.
And the fuzzy logic that's controlling the actuators to centralize the wriggle. How does it work? Have you considered turning and the stresses and the asymmetric hoop stresses that come?
Yeah, yeah, it's a very good question. Absolutely, we've considered turning. So for the synchronous machine where we're excavating a tunnel at the same time, we think this process can go around far tighter radii curves than a conventional system. So the shield is much shorter. And the shutter we've sort of plumped on 3 meters. We don't want to reduce it much more than that because there are still high forces in play which need to be contained. The shutter itself is articulated so that it will be bent to the ground. So the ground is the external force which will bend it. In terms of the non-synchronous, the relining process, again, we have no concern about that because on the outside of a curve, obviously you have to place more material. There's more material on the outside of a curve. That's absolutely no problem for the injectors because they just, as happy as Larry, they just carry on just pumping until they get to a pressure. And so actually all the problems with the eccentric forces produced by hydraulic rams onto segments, they completely disappear. We're trying to damage this material. We're trying to crush it. So we can't damage it. And so we're absolutely confident that, if needed, I know, cable tunnels in the past have had very tight radii because they have to follow the roads. This system has the ability to go around far tighter curves than a conventional segmental lining. Because we don't have the problem with vectoring the force. And one thing I should mention is that people say, well, of course, that's fine. You keep talking about the benefit of reducing the ring build, but that's not important because we can use continuous mining. Well, all I can say is that the experience of using continuous mining has not been brilliant so far because the length of the hydraulic rams, basically being twice as long as a non-continuous miner, has caused a lot of damage on segments. So I don't know. I see Martin Nowak, and he probably won't say too much about high speed too, but I understand it was used for one Wednesday afternoon on one of the projects and then turned off. But so I might be exaggerating slightly. Is that an answer? Thank you. Oh God. Come on, get it over with. Oh no, sorry. It's my 2 nemesis together. It's a tag team. Against the ground, how do you not heat the surface? That's a very good question. And in fact, one of the things that we've not mentioned is we believe that this actually improves the ground as well. So it's a bit like compensation grouting. Compensation grouting is a very high pressure over a very small area. And these injectors, whilst they're 30 megapascals inside the injector, of course, that load gets spread. And in fact, it's about a quarter of that load by the time it gets in contact with the ground. And all of that, as Henry has taken into account. But it actually has the ability, if you've got a very non-uniform stress state in the ground, so you've got a, say a low K naught for some reason, we actually believe that the process of placing the material could actually produce a much more uniform hoop compression in the lining. So, but obviously we're not banking that, but yes, yeah. I mean, I think, do you want to say something about the modeling, the numerical modeling that you did?
I mean, yeah, so there's a bit of interplay with some of the physical testing we've done as well. So the injection extrusion tests that we've done, we've looked at the sort of lateral pressures that we get from this process as well. Use that to feed into some numerical analyses and yeah, like Colin's alluded to, it's a very localized effect. So we're not talking about a lot of pressure over a large area to cause significant heaving of the ground, but we think it would be a benefit to the ground in weaker grounds and potentially give some reduction or further reduction. We think this process overall is good for low settlements, but give further benefit in that way as well.
Just a second. One for the AV tech. Can we have the second roving microphone working, please? This is not working. Hello, hello, hello. Hello.
I'll get a second.
All right, okay. Let's choose one.
Oh, Charles, you can't ask a question now.
Right, hear me. I did say I wasn't going to ask a question, Colin, but I could. You know what I'm like. It's really a logistics issue. You in your presentation talking about mixing the concrete at the front, and probably in the TBM backup.
Yeah.
Been in concrete all my life. And I know we're mixing the equipment. Now, what sort of volumes are you're talking about mixing? And number two, because of this idea of mixing the concrete within the tunnel, you're going to be restricted to the minimum diameter you can go down to. So have you looked at that? Have you looked at the equipment?
Yeah, I mean, both surprisingly good questions, Charles.
Thank you. Not as stupid as I look.
No, you're absolutely right, and this has been really the principal discussion with Robbins that we're I'm a tunneling contractor. Henry's worked for we are tunneling contractors. We know this is not about theory. It's not about laboratories and lab tests, and for sure there's going to be some challenges ahead. But what we're absolutely sure about is that putting it in bullet trains or pumping it is not going to be able to deliver the benefits of this system. So we have to mix at the face. In fact, Birmingham University had a project a couple of years ago, I think it's called Extrude, where they were looking at using extruded linings for microtunneling. Their approach was accelerated concrete, which was pumped in. So that might be all right for a 100-meter tunnel or 200-meter. We're interested in long tunnels. But absolutely the logistics is key. I have to say that I don't know if Robbins are underplaying it, and we know Robbins are a TBM manufacturer. They're not a tunneling contractor, but they've got a huge amount of experience. And so the proof of concept tunnel that we're likely to build first is likely to be one that we're pumping concrete. We're pumping the STLM from the pit bottom to the machine. Because it's just it'll be a 300-meter tunnel. It won't be a 3-kilometer long tunnel, because we need to start with baby steps. And in fact, my personal view is probably the best starting point is with the non-synchronous and relining an existing tunnel to prove it. So what was the second part?
Really, there wasn't second, but is a second part. Yeah.
Okay, I shouldn't laugh at that.
Presentation showed a comparison with Thames sideway tunnels,
Yeah,
which both had secondary linings.
yeah.
Now, Colin, you and I worked together for years on.
Yeah, I
these
did say I
topics.
didn't think they
We know
used
the
secondary
reason the
lines.
secondary lining
Yeah.
was in. It was from the Environmental Protection Agency, and that was the only reason it was consented, because we were in the aquifer.
Well,
where we
I
extract
never
it.
thought these words would come out of my mouth, my mouth, Charles, but I agree with you.
Oh, thank you very much. You can buy me a drink now.
Yeah.
All right. I've got a question online first. This is from Oeji Aloawaja and also Mike King. Is the machine adaptable for all different soils and rock types? For example, squeezing rock conditions, high water pressures, permeable gravels, open joints.
Yes. And this was actually one of the biggest areas of discussions with Robbins, that the balancing the force generated by the injectors and the face pressure, when you could be, anything from a hard rock machine where you need very high thrust forces, to say a soft alluvial soil where you have to tune it down. So that's why the process controls is controlling the number of injectors that are in play at any one time, and the speed, and that's controlled by just one thing, and that's the speed of the injector. So as we sit here today, we're saying this is suitable for any ground conditions, any water table. Yeah, so that's, do you want to add anything?
No.
Right, good.
Yeah, Christoph.
Turn it off, did he? No, he didn't. That's actually a question for Henry, for a change. You showed a diagram. I think it was a stress strain or whatever, depending on the confinement pressure which you mobilized for the material. Is there a minimum confinement pressure which the material requires to perform?
So what we've looked at, that's the envelope, that's looking at the sort of constitutive law of the material. In the actual process, what we've got is a sort of multi-axial state of stress. So there's always this continuous longitudinal thrust that's happening from the injection process. That's going to be there at the very early age, as well as the developing hoop thrust within the material. I remember this material was forced into the annular gap between the slipform shutter and the ground. So it's pushing itself out. It's generating a sort of a confinement of itself. So that's bringing us some benefit. But even when we've done uniaxial tests, no confinement whatsoever, we're getting very good strength and stiffness behavior of this material immediately after stripping.
So the confinement is not necessary for the material to work in the first place.
Not necessarily for the material
Okay.
to work.
Now, I've actually a second question. That's for you, Colin. What are you doing with TBM torque?
With what, sorry?
Torque.
Torque.
Yeah.
I mean, we would see that with the castellate at the back of the shield has a castellated profile that we would think that would be the ultimate torque resistor, because there is so much of the concrete in contact with the bulkhead at the back. There's no way that it can cause the machine to roll like you would have with a conventional TBM.
Okay. Thank you.
Thank you.
Okay.
Hello. So thank you for the presentation. I just have a small question about like tunnel openings, and like if you want to connect tunnels together or with shafts, and then how does the material work with tunnel
Who
openings?
invited you? Yes, that would have to be a special design. We realistically, and people have tried to put bioreinforcement in extruded linings. We think that's a really stupid thing to do. And so there would have to be a bespoke arrangement. So, and we see, on projects nowadays that, linings, which perhaps have not made any segmental lines, have made no provision for a cross passage using, shear boxes and various techniques. You can engineer an opening, but yes, the lining itself would not be suitable for without supplemental permanent or temporary works.
Hi, Colin. I joked with you beforehand about having some rotten fruit and some tomatoes ready to throw.
Yeah.
But can I just congratulate you on a very good presentation? And I wrote down some questions as you were going through, and I think you've answered them. And I can personally see that there are solutions to all the things that are going to be raised. So this isn't a question, it's just a congratulation on your tenacity and pursuit of this over the last few years.
I'm filling up now, Chris.
Well, I really hope that there's a client out there that will grab the opportunity to give this a go.
Yeah.
And that seems like the last step.
Do you know what? The World Tunnelling Congress this year, we saw client after client after client talk about sustainability, but not putting their money where their mouth is. And we just think, you know, it's about time somebody, because this is a huge good news story for somebody, if we can get it to work, which I'm sure we can. But
Well, I mean,
thank you for the.
No, I genuinely think there's people online and in this room who might be able to take away the message that this probably is a system that's going to work, and it just needs a client to try it.
Yeah.
So good luck with that.
Thank you.
All right, one at the back there, Divik. Been hand up a long time. I'll get you next.
God, David.
Thank you, Divik. Chris Pearson, I'm an independent materials consultant. And thank you very much, Colin and Henry, for a super presentation. You know I'll be interested in the materials, and I've visited your lab and seen some of the things you're doing. As I understand it, the process still ends up with a permanent single pass lining. So it's got to be designed for permanent works. You haven't said anything about how you might produce the test specimens that you need for the typical material parameters that are used in the single pass lining or fibre concrete lining.
Yeah.
Can you tell us something about that, please?
I mean, the little test rig that I mean, to begin with, we started with 1,000 kilonewton actuator and huge test pieces. The new benchtop rig, what I expect to happen is that Henry will receive a call, and in his briefcase, he's got this little benchtop rig, and he'll go and test local aggregates, local materials, because obviously we've got to take, you know, we're not going to be transporting materials around the world. So to do the characterization, we've actually now got a pretty good handle on that. And one thing that we've not mentioned is this process, all of the results that we've shown today, we're pretty confident are lower bound values, because the specimens have attitude. And when you unload them, they basically bounce back because of the steel fibre. And so any strength, stiffness, permeability, anything that we're measuring with steel fibre in, we think is actually the lower bound because of the stored energy in the system. And, you know, just in front of you, you've got the pride of master builders. And, you know, I think as the chief engineer of Hochtief said, as we all know, I mean, concrete has changed immeasurably now. And we're benefiting particularly from the logistics, the pumpability, the rheology, the open time, the bleed characteristics. I don't know what any of those words mean, by the way, but Henry told me. And you know, we're benefiting hugely from those things. Do you want to add anything?
Yeah, so the benchtop test rig was kind of developed as, I mean, partly we can make a lot more samples a day in it. With the larger rig, it was kind of do one test a day. You know, we can do sort of 8 tests, 8 samples a day with the benchtop test rig. And also thinking ahead to when you've got to do this as part of an actual tunnel construction process, you've got to do all the quality assurance processes and everything like that. Being able to rapidly form samples, do that sort of quality control testing is going to be essential as well. So that's going to be the tool we're going to be using.
What about the typical notch beam test that would be used to derive the residual strength parameters that you might use in a fibre concrete design?
I think we're going to need to talk to you, Chris, because yeah, making an extruded sample for testing in flexure is a challenge. So potentially we could extrude it in into a rectangular or a circular mold and then cut them down for testing. I mean, essentially, we're thinking that the action of crushing and placing only enhances the properties. So for a control test, it might be just take the constituents and cast the samples. That might be one simple solution, because I mean, I don't know if you've thought about how we could extrude beam samples, but it wouldn't be easy.
An interesting one. Seems to me you've got this. It's a bit like spray concrete, where you can't really test the stuff that's in situ.
Yeah. I mean, there are certain aspects there, and certain, there are certain similarities, and looking at the strength gain, and people kind of get lost in the numbers. There's been a lot of interest in printed concrete. This is 1,000 times stronger in its early age than printed concrete. So the axis is in megapascals, not in kilopascals. The strength is way above the modified J2 curve in its early age up to. And one interesting thing is, of course, it has reduced stiffness, but from a soil structure interaction point of view, that's possibly not a bad thing. Putting very stiff linings in the ground is obviously attracting load. So, I mean, there's a huge amount of work, and we would like to work with, not you, Charles, but a few people. No, we'd like to work with the industry to make this happen. Only joking, Charles.
That's great. Thanks, Colin.
All right, there's one down here. Yep.
Thank you, Colin and Henry. Couple of just observations, but I'm sure you came up to that decision. One of the things you showed was the concrete was 40-50. You chose that strength for whatever reasons. Did you do a parametric study to understand which is the best concrete strength you should be using? That's sort of first question. To follow it up, one of the things that you have is usually, we didn't talk about the thickness of the lining, but within that, if you did have a huge temperature difference, high temperature difference between that cross section, you did show a log time against a strain curve. You've got an elastic strain and you've got a thermal strain.
Yeah.
How did you accommodate that in the analysis?
Do you want me to take the first part? You said the second. Okay, so in terms of the optimum strength, you'll be aware that precast concrete segments, they have typically 460 kilograms, 450, 60 kilograms of cement in them, so that they can be stripped at early age. And in the long term, and Charles, I'm sure will back this up, quite often we're seeing segments over 100 megapascals. Now that's not needed and it's not helpful. I mean, it's perhaps going off on a little bit of a tangent, but I visited the Channel Tunnel the day after the last fire, which was, the concrete segments were probably, I think there was a suggestion they could have been 120 megapascals. And in the fire, they were incredibly brittle. They didn't have any polypropylene fibers in. So, we think that the strength of 40-50 is not a bad place. I mean, that's a sort of 28-day average value. We don't think that that's a bad place to be. And, quite comparable with, it's adequate, I think, because as I mentioned earlier, you sat next to Alan, a former colleague of mine at Warwick, and when we're teaching the students about segment design, and they'll do an interaction diagram, and they'll work out that the lining needs to be this thick, it needs to be 100 mil thick, and they're right, they've done the forces, and that's the MN diagram shows 100 mil thick. But of course, you can't get the gasket in, you can't get the bolts in, you can't get the fixings in. And so what we have is just the slipform lining is just what we need. We're not having to make it thicker because we're accommodating all of those other things. In terms of the thermal characteristics, do you want to mention that?
Yes. So in the shrinkage testing, the samples have been in the laboratory environment. So we're monitoring temperature and humidity, but those shrinkage curves are done in sort of ambient lab conditions. Yes, for lots of large changes. There will be thermal strains in temperature, and we'd have to sort of assess that on a case by case basis. But its characteristics at that stage are like a dense concrete. So that's kind of the properties that we're expecting really there.
And I think as far as the process is concerned, bearing in mind we've got very little cement and no accelerator, so we're not the temperature of these mixes which Henry has measured is it's nothing like conventional concrete. It's much lower. And I think Henry mentioned it. Shrinkage is absolutely everything here, because we're going to have a huge amount of external restraint from the ground because we're pushing this stuff against the ground. And if this shrinks and it cracks, we know that if those cracks are over 0.1 millimeter, they're going to let water in, and the whole concept of one pass lining goes out the window.
Yeah, I mean,
so
outside, the interface with the soil, yes. But if your temperature is very high, and I know one of the things that we said was nuclear reactors in whatever format that we are trying, that difference is very, very high. So suddenly you have a big nonlinear gradient.
Yeah.
And how do you accommodate that?
I have to confess, I mean, we've not looked at high temperature applications at the moment, but it's something that we can look at.
Thank you.
Thank you.
Okay, so we'll have to call it a day now, but terrific presentation, Colin and Henry, and definitely deserved the revolution in the title. And if we can all put our hands together, show appreciation. Just a couple more announcements, and then we can all go down to the bar. Which is sponsored tonight by Beckart and CECL. Thank you very much. Thank you very much. Okay, Jeff Clark, Tunnel Engineering, Clarky as he was known. So sadly he passed away late November after a very short, sudden, unexpected illness. Those who knew Jeff, he built up Tunnel Engineering to provide in top quality tunneling equipment for the industry, our specialist industry. And it was always a great pleasure to work with, to deal with, always got a smile on his face and always had huge enthusiasm. He leaves behind many, many friends. His daughter and son-in-law are continuing with the tunnel engineering. And his funeral is next Thursday, the 18th of December, just north of Manchester. Details can be found if you contact the BTS, if you're interested and like to attend. And another one, sadly, we've missed and lost recently, Barry Sylvester. So sadly passed away last Sunday after a battle with cancer. He was only 59. Baz, as he was known, started as an apprentice fitter for Fairclough Tunnelling. He developed into a first-class talented fitter, working on many tunnel projects as Fairclough morphed into AMEC and then Morgan Sindall. One of the good guys, commanded a huge amount of respect in the industry. Funeral arrangements will be posted once confirmed, and yeah, for both those two people, I've heard nothing but great comments and sadness. Okay, moving on then. So our January presentation is on HS2, lots S1 and S2, and talking about large propolis openings in segmentally lined tunnels using special segments. And then in February, joint meeting with Min South, and that is on collapsed segmental line tunnels and the recovery of it. Then in March, we have our Harding Prize. So applications are out now for engineers under 33 to submit a paper. I've said this in the previous times. It's very hard sometimes to get a paper submitted because it goes through HR departments, publicity departments, and they're all a bit sensitive about what's said and done. So I'd ask people who head up these organisations to be sensible about this and encourage our younger engineers to submit papers rather than trying to put barriers in the way. It's terrific competition, and the more people enter, the better. So yeah, support on that one, please. And the guide to sprayed concrete lining has been published. The guide will be available free to download through Emerald Publishing as a single PDF. And there'll be more details on this and a short presentation at our January meeting on it as well. Next year, the biannual BTS conference. It'll be at the Queen Elizabeth Centre just around the corner, 6th and 7th of October. So a date for your diary there. Another date for your diaries, please. The very popular BTS Design and Construction course at Warwick University. Several lecturers here. 6th to the 10th of July. Bookings will become open on the 26th of January. Those looking for stocking fillers, BTS at 50 book is available. Marvelous present. Yes. Okay. And membership. If any of you are not members, BTS, it'd be lovely to have you join. The more people we got, the better, the more involvement. Only £93 a year. And also young members as well. So there's a QR code there and the website. Almost there. The annual dinner, that will be open for bookings 1st of February 2026. Yeah, and it is the first Friday after the first bank holiday in May. Back to our normal date, usual venue, the brewery. Sadly, we won't know Mr. John Scoley there. And that was him. Typical pose, flamboyance, wishing everyone a Merry Christmas. And from myself and the British Tunnelling Society, wish you all very good Christmas and a Happy New Year. And now we're going to spend some of your money. Thank you.